Today we're looking at an introduction to coordinate proofs with triangles. Now over the next few lessons we'll be doing coordinate proofs with other kinds of quadrilaterals like rectangles or parallelograms. But today we're really just focusing on triangles so that we could find some additional properties of triangles that we have not seen before. And instead of just saying, here's the property, we're going to work through explaining or showing the property is true by demonstrating a coordinate proof. So some of our homework will be based upon coordinate proofs over the next couple of days, but then some of our homework will not be coordinate proofs. We'll be focusing just on the properties and how we could set up algebra equations and solve them and so forth. Specifically with the triangles that we're looking at today, we're going to talk about something called the Midsegment theorem, which we saw briefly in our previous chapters. Let me grab that old pack of notes and just remind you that we have seen this before. This was back when we were talking about trapezoids. So here's the picture I want you to look at here. And we said that if you have a midpoint on the left leg and a midpoint on the right leg of the trapezoid, then you create a segment in the middle called a midsegment. And so what that means then is that it is going to be parallel to the bases. Now, there's two bases on your trapezoid, of course. And on our triangle, there's only one base. But it should still have the same quality. It should be parallel to the base. We also took a look at our trapezoid and said we could calculate the length of that midsegment by finding that the length is going to be equal to the average of the bases, half of the sum of those bases. So in a similar way, we're going to compare the length of this triangle's midsegment to its base, and we'll see how they compare as well. Now, normally we put the base on the bottom, but we're not doing that here. The base doesn't have to always be on the bottom because we can rotate an object any way we want. So the way we're positioning this is we are saying that the base is this upper left side, and this will be the midsegment. So this is what we're given. We're given the triangle OBC. We know that this point at the origin is 0, 0, and we're provided this coordinate point at point B, 2Q, 2R. And we're provided this coordinate point at point C, 2B, 0. And you'll notice we're not using a numerical set of values. We're using variable coordinates instead. So we're not solving for Q, we're not solving for R, we're not solving for P. But because of the variables, if we can prove it with the variables, then that means it will always be true with numbers. Right? So this is not just an example, it's a legitimate proof. So we're told that point F is the midpoint of OC. Remember, this is given information. So if point F is in the middle, we can put tick marks on either side. And we're told point E is the midpoint of segment BC, so we can put tick marks on either side. So if you connect midpoint with midpoint, that is your midsegment. So let me label that midsegment, and that means we're comparing the midsegment to this upper left-hand side. They look to be parallel, but we're going to prove that. So we're calling this the base of the triangle. All right, so the height would be perpendicular to the base, but we don't have to worry about the height. It's just that we've taken the triangle, we've rotated around, and we're calling this upper left side the base. So because the midsegment had two properties on the trapezoid, we're going to find that it also has two properties here on the triangle. We have to prove that the midsegment, FE, is parallel to the base of the triangle, segment OB. And we're also going to prove the length of that midsegment is not equal in size, but in fact is going to be half the size of the base. And you can see it is smaller. It is smaller than the base. It's going to be exactly half the size of the base. So those are things we have to prove. Now, in order to prove those, we have to use the coordinates at point F and point E. And we don't actually have those coordinates provided to us. So we have a little bit of preliminary work just to get ready to then show these two qualities are true. So first of all, we have to find the coordinates of point F and point E. So point F, we were told, is a midpoint. that means we can use the midpoint formula. So I'm going to calculate the midpoint, and I'll label it with the F, saying this is the midpoint of point F. All right, so here's my midpoint formula, and the midpoint formula says we have to add up the x-coordinates and divide by 2. We'll add up the y-coordinates and divide by 2. So this is the midpoint of this edge from O to C, OC, and F is the midpoint. So find your x-coordinates. We have a 0 and a 2p, so 0 plus 2p. Find your y-coordinates. We have a 0 and a 0, so 0 plus 0. This means that we will end up with 2p divided by 2, which will give us 1p, and 0 plus 0 divided by 2 is 0. So now we know this point F is located at p comma 0, which makes sense because if the total distance is 2p, then half of that is 1p, and it has to be half because you have half on either side. A midpoint creates 2 equal halves. This will be now point E. So the midpoint to find point E is, so now we're on the right-hand side. We need x-coordinates of 2q and 2p. So we're going to add up 2q plus 2p, all divided by 2. And now the y-coordinates, we have a 2r and a 0. 2r plus 0, all divided by 2. So these are not like terms. They don't combine, of course. So we can divide them by 2. 2q divided by 2 and 2p divided by 2 give us 1q plus 1p. There's your comma, which means this is the x-coordinate at point E. And 2r plus 0 is still 2r. Divide that by 2 and you get 1r. This is your y-coordinate at point E. So I'm going to label that on the diagram. The x-coordinate is q plus p. There's the comma, and the y-coordinate is r. All right, so now that we have all of our information, we're ready to start proving these qualities. So the first thing we want to prove is we want to show that the midsegment FE is in fact parallel to that base OB. All right, so we know parallel lines have the same slope. So what we have to do is check their slopes. We want to know, do they really have the same slope? Let's find out. So here's my calculation, M for slope, and I'm going to label this. Again, this is for segment FE. We'll do our slope formula, and then we also have to calculate the slope for segment OB. All right, so 2 calculations to compare the 2 slopes. So let's focus on the midsegment FE. Here it is. All right, so remember we're finding the slope. The slope formula is y's over x's. We need to find the y-coordinates. We have an r and we have an o, so r and o. So we have on the top r minus o. And then on the bottom we have x-coordinate minus x-coordinate. So here this x-coordinate is q plus p. So q plus p is the first x-coordinate, and then we're going to subtract the other x-coordinate, which is the letter p as well. Our takeaway 0 is still r. And on the bottom, you can see p minus p drops out, and that leaves you with q. Now again, we're not solving for r and q. We just want to know, will we get the same answer when we find the slope of segment OB? All right, so here's my slope formula. We want the y-coordinates on the top. We have a y-coordinate of 2r and 0, so 2r minus 0. Now the x-coordinates on the bottom, we have a 2q and a 0, so 2q minus 0. So when you subtract 0, you still have 2r and 2q. And the 2 divided by 2 gives you 1, so it's 1r over 1q. And look at that, they are exactly the same. You have r over q and r over q for both. That means the slopes are equal. So anytime we're trying to prove a property, we always summarize what we've found with a conclusion. In other words, we're going to interpret the results. What do these results mean for us? So what we do is we kind of restate the thing we had to find. Segment FE is parallel to segment OB because, all right, so now you have to interpret, what does this mean? Or how do we know these are parallel? Because they have the same slope. Or you could say because they have equal slopes. So when we're doing a proof, we're always going to use, when we're doing these coordinate proofs, we're always going to do some calculation either with midpoints or slopes or distances, and then we always summarize our findings with that conclusion. So that's the first property. Yes, this midsegment really is parallel to a side of your triangle, what we're calling the base. Now we want to compare the lengths. We know they're not equal in length. One is smaller, one is bigger. But what we're saying is that the property states that it is exactly half the size. So we need to find the two lengths and compare those lengths. That means we need the distance formula. So I'm going to start off with finding the length of FE. Now notice there's no bar above this because it's not just the name of it. We're actually talking about the length of it, so we have a numerical value represented by these coordinates. So here's my distance formula. All right, we need our x coordinates from point F to point E. So here we have our point F, the x coordinate is a p. Here we have an x coordinate, which is the q plus p, and we need to subtract those. So it doesn't really matter what is your first point, what is your second point. I'll take the q plus p and I'll subtract this p. It'll be a little bit easier on our algebra. So here's my x coordinate of q plus p, and I'm subtracting the other x coordinate of p, and all of that has to be squared. So that's x coordinate minus x coordinate quantity squared plus. Now the y coordinates, we have an r and a 0. So r minus 0 quantity squared. So again, you can see that the p's cancel out. So that means you have q squared plus r squared. Now we talked about the rules of simplifying radicals. You're not allowed to simplify the radical with that plus sign in there. Your next step would be to combine like terms, but these are not like terms, so they cannot be combined. So we cannot simplify, we cannot proceed. That is as far as we can go. Now for the length of OB. All right, so we want the x coordinates. We're looking at this side of the triangle here. We have an x coordinate of 2q and an x coordinate of 0. So 2q minus 0 quantity squared plus. And the y coordinates are 2r and 0. And so when you subtract the 0, you can see we have 2q quantity squared and 2r quantity squared. So we could square each of those, and that will give us 4q squared plus 4r squared. Now again, we're trying to compare the lengths, and we're really not quite ready to compare the lengths. They're obviously different, so we know they're not equal in length, but we're not quite at the ready to show that one length is going to be exactly half the size of the other. So we have to manipulate this slightly. All right, so I'm going to continue on the next line here. And I'm going to take that 4q squared and the 4r squared and say, hey, you know what? They have 4's in common. Let's remove a common factor of 4. So here's my 4 in front of the q squared plus r squared. We just factored out the 4 and parked it in the front. Now you'll notice, because we're now multiplying, we can now simplify the radical. We're allowed to take the square root of 4 independently of the square root of the q squared plus r squared. So we could take the square root of 4, and that gives us 2 times the square root of q squared plus r squared. So what I want you to do now is compare these two. You'll notice that they look exactly the same, except this one is 2 times bigger because it has a 2 in front. It's 2 times the radical that you see above. That means this length of FE is half the size of OB, and OB is 2 times bigger than the length of FE. And that's what we're seeing right here, right? One of them is half the size of the other, and that's the case here. This is half the size of the other. And so we're going to now write our conclusion. I'll fit it in right here. All right, and so we'll say FE is half the length of OB because FE is radical q squared plus r squared, and OB is 2 times bigger than that, right? So 2 times the q squared plus r squared. So what we've done is we've taken this mid-segment, and with the variable coordinates, we've proven the properties. All right, so this is what a coordinate proof looks like, and like I said, we'll be doing more of these in the days to come. Maybe not as quite detailed as this, but there's other questions we can ask. And this is really just meant to be kind of a showcase piece so you can see what a coordinate proof looks like, but at the same time, we're verifying that, yeah, this mid-segment theorem is the real deal. So we're going to summarize that down here in the box below, the mid-segment theorem. Here you can see the way this is drawn. They put the base on the bottom, and there is your mid-segment in the middle. We know it's a mid-segment because you have tick marks on either side of the point. That would be the midpoint. So you're connecting midpoint to midpoint. All right, so the segment connecting the midpoints, that's this one, of the 2 sides of the triangle is, first of all, parallel to the 3rd side. Here I'm calling it the base, but it's parallel to the 3rd side and is half as long as that side. So let's take a look at some diagrams where we can apply these properties. This is example 2. All right. Here is our triangle. They're telling us segment DE is a mid-segment, so we know it's connecting midpoint to midpoint, and we want to find the value of x. So here the 11 that you see, that is the length of the mid-segment. Now we learned that this mid-segment is smaller. It's exactly half the size as the side of the triangle it is parallel to. So these are your parallel parts. So that means the side of the triangle is bigger. How much bigger? Exactly double the size. The mid-segment is half. The size of the triangle side, and the side of the triangle is double the mid-segment. So we're going to double the 11, and that'll give us 22. All right, so that's what we're doing in these next couple of examples. Part B, again, here is your mid-segment. It is parallel to the bottom edge of the triangle. The bottom of the triangle is what we know. It's obviously bigger than the mid-segment. How much bigger? 2 times bigger. So we need to cut that in half to find the length of the mid-segment. Half of 26 is 13. And then part C. Now again, this is your mid-segment, and this is the parallel side of the triangle. We don't have the variable on the mid-segment, so be careful. This is a little bit of a tricky problem. We're not comparing the mid-segment to the side of the triangle anymore because the variable is not there. The variable is on one side of the midpoint, right? We have a midpoint creating 2 equal sides, and that means x is 7. These are both 7s because you have point E as a midpoint, so it's exactly in the middle. All right, we're going to look at some other examples on the following page using the properties of this mid-segment theorem. All right, for example, up here at the top, we have example number 3. This is triangle WXY, and so that's a typo that I haven't gotten around to fixing. So in triangle WXY, we have these additional points, point R, point S, point T. So R, S, and T are midpoints of the side. So what that means for us is that point R is in the middle of this left-hand side. So I can put tick marks on either side. Point S is in the middle of the right-hand side, so double tick marks. And point T is in the middle, so there's a triple set. Okay, now it might look like these are equilateral triangles, but we don't know that for certain. All right, that's not given information, so you can't just look at the size of the picture and make that assumption. What we want to do instead is we want to identify what parts are parallel parts and what parts are congruent parts. I'll put some numbers in here in a moment just to kind of illustrate the point, but we don't have any values provided in the picture. So let's start off with part A. We're taking a look at segment RS, which is this horizontal piece, and we want to know what else is it parallel to. So if you're not sure, you can just take your pen, line it up with segment RS, and just move your pen up and down until it lines up with another side. And there it is, the bottom side of the triangle, side WY, is parallel to segment RS. RS is a midsegment, so it's parallel to this bottom side of the triangle. So we'll say segment WY. Jump down to part D. This is also asking for a parallel side. So this is segment XW. All right, so XW is on the left-hand side. So put your pen on that side. And we want to figure out what is parallel to this. So just move your pen right and left until it lines up with another segment. And there it is. Segment ST is what it is lining up with. So the left-hand side and segment ST, that is your left side of the triangle, and that is your mid-segment that is parallel to the left side. So that is segment ST. Parts B and C are not asking for parallel sides. They're asking for what is going to be congruent. All right, so let's think about this. In part B, we have segment WT, which is here on the bottom left-hand side. We already put a triple tick mark on that, and so we can see if point T is a midpoint, then segment TY is also going to have that same length. But apparently there's yet another piece of information. So this is where I'll bring in the numbers just to illustrate the concept. Let's pretend for a moment that the length from W to T is a length of 4 units. That means if T is in the middle, you'd also have another 4 units on the right-hand side. That means this entire bottom edge of the triangle is 8 units. Okay, so let's pretend that's given information. 4 on the left, 4 on the right, altogether 8. We're going to compare this bottom side with the mid-segment. Remember, the bottom side is parallel to segment RS. So this is your mid-segment. We've learned that the mid-segment is smaller than that side of the triangle. How much smaller? It's half the size, right? So half of 8 gives you 4. Look at that. You have 3 segments that happen to be the same length. On the left side of the midpoint, on the right side of the midpoint, and the mid-segment itself, which is RS. All right, so that's the concept. Let's see if we can do that again without numbers. So they're starting us off with segment RT. Segment RT is this left-hand mid-segment, which means it's going to be parallel to this right-handed side. This right-handed side has double tick marks on either side of point S, which means these 2 pieces individually are equal to the segment of RS. Remember, you need 2 of these segments RT to add up to one full right-hand side. Again, we could pick numbers to see if it makes sense. If this is 3, and this is 3, and this is 3, then 3 plus 3 is 6. Do we see that pattern where the mid-segment is half the length of the right-hand side? We do. So you can see that these 3 segments are congruent. So we have segment RT, we have segment XS, and then we have segment SY. So now we're taking it a step farther. We have pretty much the same diagram, different letters here, but you can see it's pretty much the same picture, but this time we're going to be labeling certain parts of the diagram with expressions so that we can set up an equation and actually solve for missing parts of the triangle. So let's start off with part A. Here we're saying that segment AB has a length of 2x plus 14. Now AB is your mid-segment, all right? So that is your 2x plus 14. And segment GJ is x plus 34. So GJ is that bottom edge of the triangle. So that is your x plus 34. So in other words, you're comparing a side of the triangle with its mid-segment. And we know they are not equal in size. One is clearly smaller and one is clearly bigger. So we have to figure out, how do we build an equation if they're not equal to each other? So remember that you're going to take the mid-segment, and because it is smaller, you have to double the mid-segment to equal one of the triangle's sides, right? In this case, we're talking about the bottom side only. So because the mid-segment is smaller, it is half the size, you have to double that midsegment to equal the length of that bottom side of the triangle. So we're going to double that 2x plus 14, and that will equal the bottom side, which is the x plus 34. So in setting up your equation, you have to figure out what side are you doubling. Are you doubling the left side or the right side of the equation? Well, it depends on where you put the midsegment. You have to double the midsegment, and that way you can double the information they give you, which in this case is the 2x plus 14. So I'm going to distribute the 2. So we have a 4x plus 28 equals x plus 34. We're going to solve for x by subtracting x from both sides. So minus x, we get 3x plus 28 equals 34. And then we're going to subtract 28 from both sides. So 3x equals 6. And now we can divide both sides by 3 to isolate the variable. And now we know x is 2. We're not quite done because they're asking for the actual length of segment AB. So let's plug 2 back in. If AB is the 2x plus 14, then 2 times the value of x plus 14. That'll give us a total length of 18. So in other words, if this is 18, then that means from G to C, this should also be 18. And then C to J is also 18. And 18 plus 18 is 36, right? And you can see that 36 is, in fact, 2 times bigger than the midsegment of 18. Yeah, so that works out. So let's take a look at one more example. We'll do part B here. All right, so in this case, we're looking at segments AC and HJ. So AC now is going to be this left-handed midsegment. So it's the smaller piece. And the HJ is the right-handed side. It's the larger piece. So again, you want to find your midsegment and you want to double it. You want to double the midsegment, and that'll equal that one triangle's side, in this case, the right-hand side. So my midsegment is the AC. So we're going to double the segment called AC, and that will equal HJ. That's what we're describing right here. So let's double the 6z minus 7, and that will equal the length of that right-handed side, HJ. All right, distribute the 2, so 12z minus 14. I'm going to move all of my z's to the left-hand side, so let's subtract 9z from both sides. We get 3z minus 14 equals negative 5. Now add 14 to both sides. We can move all the constant terms over to the right-hand side. We're going to add 14 and we get a 9, divide both sides by 3 and we get z equals 3. So we're going to plug that back in to find the length of HJ. So HJ is the 9z minus 5. And that gives us a result of 22. So let's finish up with the vocabulary on the very bottom part. This is talking about a new kind of segment called the median of a triangle. And so the median of a triangle is going to be a segment that will connect the vertex, all right, so this is vertex, to the midpoint of the opposite side. So these are adjacent sides. We want the opposite side. So we're looking at the opposite side, and we want to find the midpoint of the opposite side. So we're just eyeballing it here, and let's call that the midpoint. We'll put tick marks on either side so that we can just visually confirm that's my midpoint. We're going to connect those two, and that is a median. That's what we call the median. So we are going to draw all 3 medians because there are 3 vertices. All right, so again, here is the left vertex. We want to draw a median to the opposite side. So I'm just going to eyeball the midpoint is here, put tick marks on either side, and let's draw this median, like so. There's a 3rd median. So here's the vertex on the bottom right side. We're going to draw a segment to the opposite side and about to the midpoint on that upper left side. Now, if we constructed this precisely, which this is just not this is not a construction here, but if we constructed it precisely, all three of these medians would intersect at a common point. Right? Since I was approximating where those midpoints were, I wasn't entirely accurate, but this is the concept here. The three medians will intersect at one point.